Start recording now. Good. So good afternoon. Well, good morning, everybody. Sorry about this problem earlier with the link. We have Vangelis Panos with us, who is going to go into the details of Simplex and Barrier's options for times models. So since we had this delay, Vangelis, please go ahead. We can start, and then please keep on all your questions or send them on the chat box, and then we can discuss at the end of the presentation. So Vangelis, please go ahead. Thanks.
Thank you, George. Thank you, Paul, for this opportunity to present some Simplex barrier options for the times models. And as we all know, our models become more and more complex over time. If we look 50 years ago when everything started, the models that we had at that time seem to be very simplistic to what we have today. So exactly this is the point of this webinar today, how we can speed up our models with, which I'm talking only about linear programming. I'm not touching mixed integer programming here. So I'm going to cover in this webinar some insights on Simplex Barrier, what is behind the box. Then we will go through a practical example. We will take it from the beginning, and then where it took a lot of time to be solved. And then by changing Simplex barrier options, we made possible to reduce the solution time. Then I would also like to touch a little bit the use of advanced bases in Simplex algorithm, not in the barrier. But I will not be able to cover in this webinar because of time constraints. Issues related to how we deal with numerical difficulties or degeneracy, or how do we assess the quality of the solutions that we obtain. I will reserve this for a second webinar. So I will start with a few words about the Simplex barrier algorithm, and a convention that I'm going to have in this presentation is that whenever you see a red font underlined, this means that it's a Simplex parameter there. And when you will get this presentation, this is clickable. So if you click there, then you will go to the corresponding section in the manual. So a few words about what is the difference between Simplex and Barrier. So probably we are all familiar about how linear programming optimization works. So we have learned that when we are using the Simplex algorithm, the constraints of our models form a feasible area where the solution, the optimal solution is found. And according to the theory, the optimal solution should be in one of the vertex of this polyhedron. And what the Simplex algorithm is doing is trying to move from edge to edge until it arrives to the optimal solution. But it has to examine all these vertices, and a theoretical crude maximum number of vertices is given by a combinatorial formula. And this implies that the number of vertices that needs to be examined by the Simplex algorithm can increase exponentially with the size of the model. And here comes the interior algorithms like the Simplex barrier, which instead of moving from edge to edge until they arrive to the optimal solution, they just cross the feasible area and they take, let's say, a shortcut. And as you can see here, a barrier algorithm has two major, let's say, mechanisms. A predictor or a growth, which is this, what color is this? Yellow color here, which tries to move towards the objective function. And a corrector, which is this green arrows here, which tries to correct the algorithm so that it doesn't hit to an edge, because if it goes there, then it's very difficult to reach to the optimal solution. So this is how barrier works behind. And the performance of the barrier, of the Simplex barrier algorithm, is influenced by these four main elements that we often see it in the barrier log file. And I hope that this log file is visible. If it is not, then I will make a zoom. Please let me know, George or Paul, if this is visible.
It is, yeah.
Okay. Then, so we have the number of dense columns, the total non-zeros in factor, the total floating point operations to factor, and the number of non-zeros in the lower triangle of A multiplied by A transpose. I will go through all these points in this presentation, but this is which numbers, when we get this barrier log, we should look to get a feeling if our model is going to take a lot of time. So it's 1, 2, 3, and 4 numbers here, which are very important. But let's continue a little bit with the differences between the simplex and the barrier. And there is one important difference here, that we can get the same objective value with simplex and barrier, but the nature of the solution differ. And the most important difference is that the barrier algorithm, because it crosses the feasible region, it relies on convergence criteria and cannot move to exactly the optimal solution. So what we have here is that when we get a solution from the barrier, this is not a basic solution. This means that the variables that we have in our solution can be also between in their bounds, but also at the bounds as well. And for that, we need the crossover algorithm to be invoked. So the crossover transforms a typically near optimal barrier solution to an optimal extreme point solution, to an optimal solution which lies on the vertex of this polyhedron. And the crossover algorithm does not benefit much from the parallel hardware. This is the problem, and it's time consuming, especially when it is initiated at a point where it's very distant from the optimal solution. This is very important. So from the moment that barrier does not produce a basic solution, we cannot use advanced start basis. So we cannot initiate the barrier algorithm with a point which is quite close to our objective function. This is not possible. Another difference is that the barrier requires significantly more memory than simplex. It works well when the model matrix, the product of model matrix transpose with, multiplied with the transpose model matrix is sparse and can also solve degenerate problems, but it's sensitive to the presence of unbounded optimal phases. But from all these points, the most important that I want you to keep is that we don't have a basic solution. And what does this mean, actually? Let's see an example. And on the left side here, I have the CPLEX barrier with a crossover. And I get, in the end, this objective function after solving the model for 8 minutes and 30 seconds, while without invoking the crossover, the solution time drops to 3 minutes and 30 seconds. And if I take the difference between the two objective functions, I can see that it's very small, which means that we get almost the same objective value. But the nature of the solution differs. And we can see this in this example here, where here I have the fout parameter. This is the var fout in Veda, but I read it directly from the GDX files that is produced by the end of the time solve. This fout here is when we have the crossover, and this fout here is when I don't invoke the crossover. And what I see here, and this is the difference with the basic and non-basic solution, is that I have in the second case, when I don't invoke the crossover, some variables into the solution, which are very small. While when the solution is transformed to a basic solution, these variables do not participate, are going to their bound, to the 0. You see, so this process that produces the flow, this flow for this time slice. So you can see here that for the time slice 5 and 6, actually it should have been 0. But the barrier without crossover reports this as a solution. Otherwise, it's pretty much similar to a certain precision. So we can see, for example, here and here, that it's very similar until to the 6th, 7th digital after the decimal. And now a little bit insights on the crossover. And we can look a little bit here on the left side where we have the log. So when the crossover starts, what is happening? So the barrier finishes, it finishes with a point where the crossover will take it and start to convert the solution to a basic solution. And when we have more than one thread, then a concurrent optimization happens, which means that the CPLEX algorithm, the CPLEX solver initiates both primal and dual crossover. Primal crossover in one thread, dual crossover on the second thread. Independent of what type of crossover is initiated, if it is primal or dual, the crossover does two things. It takes the primal variables and it pushes them to the bound. And then it takes the dual variables and pushes them to the bound. And this is indicated here with dual D moves and primal P moves. So when we see here dual D moves, means that the dual variables are pushed to their bounds. And when we see primal P moves, means that the primal variables are pushed to the bound, so that the solution, let's say, becomes a basic solution. Usually when both primal and dual crossover are initiated, the log that we get is for the dual crossover. So that's why you see here dual. But if it happens that the primal solves the model first, then this is reported in the log file. And this is quite important that there is also a second step after the pushes, because after the pushes finish, then the basis is either optimal or a little bit re-optimization is needed. And you can see here, for example, that when the dual pushes are starting, the crossover needs to correct this number of variables. And as the iterations goes, these all variables are fixed. So every time the D moves here reports to us how many variables need to be pushed. You see here also something which is called exchanged. So let's see what this means also. So I would like, this is the second insight that I would like to share with you about the crossover, is that, and I will explain a little bit the primal push. And the dual push is similar. So if we have a basis, XB, then what is happening in this pushes phase is that if it is a super basic variable is a non-basic variable that is not in one of its bounds. So this variable should be someone between the lower and upper bound. So what it does, the crossover with the push, one thing it does is that either it pushes this variable to go to one of the two bounds. So this is what we saw here, pushed, or it cannot push this variable, which means that this variable needs to be into the basis. And in that case, it exchanges this variable, xj, with another variable, xi. So that's why we see here exchange. So what we get out of this log is that in the primal push phase, the CPLEX crossover needed to fix 8,000 variables, of which 12,800 of them were pushed to the bounds, and 5,000 of them were exchanged. They moved out of the basis, and another one came into that. And you can see here also the second part that I told you before, that after the crossover finishes, it can be that still the solution is not basic, and then some CPLEX iterations need to follow. And the longer that it's this number, the more time we need. And sometimes here, some scaled infeasibilities or numerical instabilities also detected and take a long time, but this we'll cover it in another webinar. And another insight that we get from the CPLEX barrier log file is that we get quite a lot of information about what is the primal, the dual objective, the primary infeasibility, the upper infeasibility, the dual infeasibility, and sometimes we got also infeasibility ratio. So what are all these things? basically the barrier internally transforms all our inequalities into equalities. And as you can see here, it transforms our problem by making equalities here. And also when we have upper bounds in the variable, also introduce slack variables. And this is the primal problem, and this is the corresponding dual problem. So all the invisibilities that are here, primarily, upper, dual, are basically calculated based on how the barrier internally is solving. So the primal invisibility is, let's say, the absolute difference between the right-hand side of our constraints and our constraints. The upper invisibility is the invisibility that we have in this equation here, how much we don't meet the equality. And the dual invisibility is the invisibility of this equation here. So this is what we see in the log file. And sometimes we have this invisibility ratio. This depends what barrier algorithm we are using. I will come to this point later. It's a little bit dark. I don't know how this is calculated. It's not reported in the manual, but what I can say is that if you have this column in your log file, then when you are going towards the objective function, this value here needs to come to a large number. You see, usually it starts always from the number 1 and then starts to increase if everything goes well to a very large number. And if we see it something like that, then we can be very happy. And this is the last inside of the barrier, and then I go to the options. So it's important to understand that in contrast to Simplex, the barrier is using relative measures and tolerances for primal feasibility, dual feasibility, and also the complementarity slackness to assess the convergence to an optimal solution. So basically the feasibility of a primal solution, and for a dual solution is similar, is assessed with respect to the variables values in the solution. So you can see here, it takes the difference, how much we violate, let's say, the constraint, and how large is our objective function. And if this ratio is less than the convergence tolerance, this is a Simplex option, the convergence tolerance, then the solution is reported as feasible. The optimality criterion is usually inside quotes because it's not so clear in the manual. And we have asked Fred Fiant from GAMS, he has asked the Simplex developers to get a little bit more insights about how this the optimality criterion is calculated. But according to the theory of the interior point algorithms, this can be based on a normalized duality gap, which means the difference between our primal objective and difference objective divided by our primal objective. And if this ratio is less than the convergence tolerance, the solution is characterized also as optimal. So it's important to note, and this is, we should have that always in our mind, that because the feasibility criterion and the optimality are relative criteria, it can be that the Simplex barrier can accept a solution with very large violations in our constraints if the solution values X are quite large. So if our objective is very large, it can be that the solution is reported as feasible even if when we have here large violations are on our constraints. This is how the tolerance of barrier is working. So it's important to differentiate between a constraint violation, which is when the difference between our constraint matrix multiplied by our variables does not meet the right-hand side of our constraints, and what is infeasibility, because infeasibility is only when we have a violation of the convergence tolerance. So if we have a constraint violation, which is very large, if this constraint violation does not make this ratio to violate the convergence tolerance, the solution is feasible. So having giving these insights on how barrier is working behind, now we can go and examine some options about the Simplex barrier algorithm to speed up our models. So I'm going to use a test model, which is a times model, a normal times model. It has some milestone years and time slices as well. And this is a pretty medium, small, depends, okay. It's a normal, I would say, model with 1.6 million equations and 1.5 million variables and around 10 million non-zero coefficients in the constraint matrix A. And if the Simplex resolve takes this model and makes the reductions and everything, then you can see that it reduces the model matrix by around 20%. So this is our test model in this webinar. And in our webinar today, we are not going to change anything in the presolve. We don't deal with what presolve is doing. So always in all our examples, the size of our model after the presolve will be around 0.8 million equations, 1 million variables, and about 8 million non-zero coefficients in our constraint matrix. So how barrier performs when we have multiple threads? And this is a question which is quite important when, for instance, we buy a new computer to run our models. So how many threads to have? And as you can see in this chart here, of course, the solution time that barrier needs reduces as we have more threads available. If we have a higher parallelization, multiple cores in our computer. But there is a point around 2022, above of which increased parallelization of the hardware does not induce in gains in the solution time, but rather it creates overhead. So when we're controlling how many threads, this is the Simplex parameter threads that we can use. It's not always wise to put -1 here, but we have to see what is our hardware, how many threads we have in our hardware. And if we have more than 20, then maybe it's better to limit at around 20. This is one important thing. So in my examples, I will limit the number of threads to 22. All right. So I take now, I would like you that you focus mostly on the log file here, and I hope that this log file is visible. I take now our test model. I solve it with barrier. And of course, I get here the statistics of the model matrix. Default options here, I just say that I use barrier and I limit the threads to 22. And then we see that the Simplex forms the dual, the presolve forms the dual. So the dual problem is passed to the barrier. And then we can see that the barrier algorithm identifies 186 dense columns, about 30 million non-zeros in the lower triangle of A multiplied A transposed. And then we have about 1,300 million non-zeros in factor and quite a large number in total floating point operations to factor. So remember these numbers here, this, and that are, and this one, of course, are important for how much will be the solution time. And if we run this model, we get the solution in 9 hours. So something is really very wrong here. And the Simplex barrier needs 5 hours. You can see it is from here. And the crossover takes 4 additional hours to solve it, to make the solution basic. So total solution time, 9 hours. First thing to note, dual formed by presolve. Let's see what is this. In the Simplex algorithm, the performance of the Simplex algorithm is influenced by the number of constraints, mostly, instead of the number of variables. And there are some rule of thumbs that it says, as you can see here, that if you have many constraints, instead of, if you have, let's say, less constraints than variables or more constraints than variables, but the ratio is quite small, then the primal simplex should be solved. Otherwise, you go with the dual simplex. But unfortunately, here we don't use simplex. We use barrier, and barrier is not influenced by the number of constraints or by the number of variables to decide if we go for primal problem or for dual problem. It's important only how many dense columns we have and how many floating point operations, non-zeros in the Cholesky factor we have. And it's important here to have in mind that when we solve the primal problem and we have dense columns in the primal problem, if we change the problem and we pass the dual to the barrier, then the dense columns becomes dense rows. They are eliminated. And the same, the dense columns in the dual problem can become dense rows in the primal problem. And it's not all, so in barrier, it's not always straightforward if the primal problem performs better than the dual problem. And it's worth it first to try this. The first option that we would like to try is, let's override the default behavior of presolve that gave the dual to the optimizer, and let's choose the primal. And if I put here now pre-dual -1 to get the primal, we see here that the number of dense columns increased, but the floating point operators to factor are 77% less. Similarly, the total non-zeros in factor, it's not 1,300 million anymore, but it's a half a billion, which means it's 60% less. And we can see here that by just doing the pre-dual, just setting the pre-dual, from 9 hours, we go to less than 2 hours solution time. And here now, that was our first option. Then we go further to the block, to the log here. And we can see, let's take now this point, dense columns. So what is the dense columns? The dense columns degrade performance. A dense column, it is a column which has a given variable in many rows. And you can see here in this chart, I did it in the cluster. I mean, this is not so easy to be produced for every model. The barrier has a mechanism to detect dense columns. And when a column is detected as a dense from the barrier takes special care so that the performance impact that this dense column has is mitigated. So it's good to be able to help a little bit barrier here to detect a number of dense columns which seem to have the less impact on the solution time. And in this chart here, I have plotted the floating point operations in trillions, and the thousands here, the number of dense columns that barrier detects. And you can see here that this is a pretty much nonlinear function that we have here. We have some ups and downs very early in the beginning. So for small number of columns, there is this behavior here. And then as the number of dense columns increase, the number of dense columns detected by barrier increase, then the floating point operations also increase, which immediately implies that the solution time will increase. So it's important to explore this area here. And this is the zoom here that I made. And you can see that when we passed the dual to the barrier, we had 186 dense columns, which created quite a lot number of floating point operations. But when we changed to primal, the number of dense columns detected by barrier increased, but the floating point operations reduced. And if we're just exploring the number of dense columns that barrier detects, we can see that if we further increase the dense columns in this particular model, we can see that it has a minimum in this point here, which we are able to get the less floating point operations. So it's worth it to be able to detect where this minimum is, and then to instruct barrier to detect so many dense columns. And so the question is how to detect now this minimum. And for this, we can use the so-called column histogram of our constraint matrix. The column histogram of a constraint matrix is a histogram, as you can see in this chart here, which displays how many columns have a certain number of non-zeros. The more non-zeros that a column has, the more dense the column is. We have a bar display option that we can use that can write this histogram to the barrier log file. And if you want to do it a little bit more, let's say, sophisticated, or you can also use the convert solver. Instead of solving the model with Simplex, you solve it with convert to export Jacobian. And then you can process the Jacobian for a histogram. And if one is interested, I'm happy to share a Python code for this. So if you produce the histogram, you can see something like this in our test problem, so that we have many columns with 50 to 100 zeros, then even more columns with 100 to 150 non-zeros, and then we have a few columns which are above 150 non-zeros. And basically, if we count how many, when we have produced the histogram, we can easily count how many columns have more than non-zeros, more than 150 non-zeros, we come to a number 2,957. I have to say that this number is produced by the Jacobian, so it's before the reductions made by Presolve. But you can see that this number here is very close to this number here, which means that this is a threshold for us to go to barrier and say, barrier, treat as dense columns whatever column has more than 150 non-zeros. And how we do that? We just set the bar colon Z option. Now, we expand our CPLEX option file here with bar colon Z 150. What happens? The dense columns that barrier detects is 2,906, exactly as much as we calculated. And what we can see here is that, as you can read here also, the summary of the improvements, is that, of course, the dense columns increased, but this, we knew it, we wanted to be increased. But the non-zeros in factor reduced by 50% from the previous case with the pre-dual case only. And even we get an additional 50% reduction on the total floating point operations. And in this case now, the solution time dropped by 30 minutes more. So we're now at 84 minutes. And there we can see that the CPLEX barrier takes about 29 minutes and the crossover takes about 55 minutes. So we can see that the crossover still has a significant, let's say, overhead on our solution time, but we will deal with that in a while. Sorry. In our if we go now a little bit further on our log file, we see something else here. We see here using nested dissection ordering. And this is the ordering algorithm that barrier uses. What is the ordering? The barrier permutes the rows of constraint matrix A to reduce the fill-in in the Cholesky factor. The fill-in is the difference in the non-zeros in the Cholesky factor and the lower triangle. So I'm sorry, I have to go a little bit back to show you this. So here we have total non-zeros in factor and non-zeros in lower triangle. The difference of these two numbers is the fill-in. When the barrier chooses an ordering algorithm, is choosing that in order to minimize this difference. So the bar order option overrides the default selection of the algorithm if needed. And we have 3 options available, which you can see according to the manual what they do. I'm not going to read them, all of them. And here we are going to get our first, let's say, the point in CPLEX. When we see in the CPLEX automatic or default, it doesn't mean that we simply select one of the available options. It's much more sometimes. So let's explore a little bit how our model behaves by changing the bar order. So you can see here that I have plotted how many non-zeros I have in factor, how many non-zeros I have in A, and how much is the difference, the fill-in. And you can see that for bar order 1, 2, and 3, you can see how much floating point, how many non-zeros I get. And we can see that with bar order 3, with nested dissection ordering, we get the best, the lowest numbers. But if I use the default option, bar order 0, which by default uses nested dissection ordering, I don't get the same number. So this is one point that even we have a default option in CPLEX, it's much more than just choosing one of the 3 available options. It does additional things. I don't know what it does. I hope that one day we are going to have more insights in the CPLEX manual on that. But since the default option works well, better not to touch it in that case. But it's good, however, to check how the different options behave before we accept the default option. Now, let's go to some, so the parameters that I just saw are the most basic ones. And now I'm going to give an additional part of tuning parameters. These tuning parameters will not affect anymore the Cholesky factor. They will not affect anymore the number of non-zeros, the dense columns, and so on. They are going to affect the performance in the iterations. And we are going to discuss the first 2. The algorithm to be used in the iteration and the estimating starting point in iteration 0. The algorithm to be used in the iterations. The CPLEX barrier offers 3 algorithms to choose. And this can be chosen by the bara-alg option. Again, we have a default. Remember my comment? The default is not always selecting one of the 3. So it says here the default is when we have an LP problem, is choosing 3, standard barrier algorithm. Indeed, the standard barrier algorithm seems to perform well in most cases. Algorithms 1 and 2, as you can see in the descriptions, can detect infeasibilities and can help sometimes in numerical difficulties. So it's good to see how our problem performs when we change the barrier algorithm that is used in the iterations. And you can, after testing in this model, we see that by forcing bar-alg3, although according to the manual, 3 is the default option. By forcing it, the solution time goes to 36 minutes. So we have a tremendous reduction here. And all the reduction, as you can see here, mostly happens to crossover. So the barrier took 21 minutes, pretty much what the number of minutes that it took before. But the crossover needed only 15 minutes this time. And the reason for that is that the bar-alg3, the standard barrier algorithm, by forcing it to use it, gave a better starting point to crossover. So this is a case where the automatic option, which is according to the manual bar-alg3, if we leave it as automatic, is not behave well, in contrast to bar order. But this depends always on the model instance. So the conclusion here is try all of them. Now, let's see the second option, the starting point of the CPLEX barrier algorithm. So again, we have 4 options to choose, and we can, it's worthy to test all of them. Usually when we pass the primal problem, as it is in this case, 1 or 2, because they try to estimate the primal, are better. And where we pass the dual, the others are perhaps more suitable. It's hard to say which one to choose immediately. So it's worth also to check alternatives for this parameter. But most probably, if you pass primal problem, 1 or 2 should be good candidates. And here, it's a little, sorry for this messy slide. It's a test how our model performs when we have bar start alg 1, 2, 3, and 4. And we can see here that with bar start alg 1 or bar start alg 2, the model, the solution time behaves quite well because we expect that we pass the primal problem to the barrier, while the others are not behave so good. And so practically the 1, 2, and I will say also 4, do not have difference. I mean, the differences that I see here in the solution time can be also because of the load of the cluster that I have. But what we can see here is that how the starting algorithm influences the barrier iterations. You can see the number of barrier iterations changes according to the bar start algorithm that is used. And also this affects, of course, what is the starting point that the crossover takes, how much time the crossover will do, and also how many simplex iterations we're going to have after crossover. And you can see here, the bar start alg 3, while the barrier time, we can claim, we can argue that is the same in all 4 options. In bar start alg 3, we have a big overhead on the crossover because of the large amount of simplex iterations that happens there. So this option here, what I try to say is, of course, it affects the starting point, but it seems also that affects where the crossover starts. Now, another point that I would like to note in the barrier iterations is that sometimes when we solve our model, we see this asterisk here, which means in this case, the barrier reverted to a previous iteration when it is to start the crossover or to just finish if we don't invoke crossover. So all these iterations here can be characterized as wasted. We can avoid them because in the end, even if it took all time to do these additional iterations, in the end, it chose, in this example, chose iteration 183. Usually when we have this type of things, can be also a presence of numerical difficulties, but I will not deal with that. I will just deal with how we can avoid these wasted iterations. So in this case, in this example, I solve the model with bar start alg 1, and it requires 38 minutes to be solved, okay, including the crossover. So to be able to see how we can avoid the wasted iterations, what we need to calculate the duality gap. Remember that this is how the solution is detected to be optimal. And we can see here the duality gap. Gap is basically the difference between primal and dual divided by the primal. And it gives this ratio here. And we can see that this ratio starts very high. Yes, our solution is infeasible, and of course non-optimal. And as we approach the optimal solution, the duality gap is reduced, and then it comes at 182 and becomes constant. And all these are wasted iterations. So what I can do now, I can change the tolerance. I can change the convergence tolerance. I can change the option bar comp. The default is 10 to minus 8. So you can see that it's not meeting this tolerance. I can increase it. I can make it to something higher than 4.5 so that I don't go to these iterations anymore. So I put it, let's say, to 4.7. And you can see here that if I change my tolerance, so you can see these are my initial options, pre-dual, dense column, starting algorithm, and barrier algorithm. 38 or 39 minutes. This depends, of course, what load the cluster had when I did the test. And then when I increase the tolerance. Yes, I increase the tolerance. Then I can see here that the iterations of the barrier didn't go to 200, but they stopped where I wanted to be stopped at around 102, 183. And the solution time is reduced. Of course, it's reduced only by 3 minutes because I had only 20. But if you see that you have too many, it's quite good to change the tolerance to avoid wasted iterations. However, things are not always pink and nice because it can be that the barrier time is reduced, but it can be also that the crossover time is increasing because we don't match exactly the point where the barrier stopped and crossover started, in this case here, by changing the tolerance. So it can be that we can worsen a little bit the starting point of crossover. So it's a trade-off between barrier and crossover time. And indeed, if the wasted barrier iterations are small compared to the total, maybe it doesn't make sense to change this. Now, let's go to some parameters affecting the crossover performance. Sorry, George, how much time I still have?
Well, I mean, 5 minutes, but it's up to you. You can continue. How much time do you think you will need?
At least 10.
Okay, yeah, we can do that. Yeah.
Okay. I hope I'm finishing soon now. So the crossover algorithm and some performance implications. So the crossover typically comprises a small percentage of our solution time, unless if it is initiated at a suboptimal interior point solution, which has a significant distance from the optimal. We saw this example just before. Or we have numerical difficulties, and then with the pushes and exchanges doesn't get a basic solution, and then significant amount of Simplex iterations needs to continue, as we have seen in the case of bar start ALK3 option that we used before. However, I'm dealing now only what we can accelerate and not how to deal with the numerical difficulties in this webinar. So we can change which crossover method to be used to reduce this time, the barrier convergence tolerance, to provide a better starting point for crossover, or even to change the pricing algorithm of the Simplex when choosing variables to enter into the base. Of course, the crossover, if we don't want it, it can be turned off with solution type equals 2. And this instructs Simplex not to seek a basic solution, and we have seen what does this mean. But it can be useful for a quick insight of the approximated optimal solution if crossover takes a long time. But I'm going now to discuss these options here. So changing the crossover algorithm. As we have seen, when we have multiple threads, the Simplex invokes both primal and dual crossover. The parameter bar cross alg, if it's set to 1 or 2, can force Simplex to use a specific crossover algorithm. And here in our test model, because we use the primal model in barrier, maybe it's worth it to see if we instruct Simplex just to use the primal crossover, what is happening. And indeed, if we force Simplex to use primal crossover only, so you can see here there is no any more concurrent optimization after the end of the barrier, but immediately the primal crossover starts. Then the solution time goes from 36 to 30 minutes. Of course, the barrier time is unaffected, but the crossover time reduced from 17 minutes in the previous slide that we have also primal and dual crossover, is reduced from 17 minutes to 10 minutes. So we are now down to 30 minutes solution time. The second option that we can use to improve the crossover performance is the convergence tolerance again. But this time, instead of increasing it, we can reduce it so that we can provide a better starting point for the crossover. And we can do that, of course, if the barrier iterations are not excessive and if the crossover also needs a lot of iteration. There is a risk if we reduce the tolerance well below the default value, then maybe barrier reports model infeasible. So in our example, we had increased the tolerance to 4.7. Now, if we, and this we saw that deteriorated the starting point of the crossover because the solution time of crossover was increased a little bit. I hope that if you go back to this slide, you're going to see it. But if we just reduce a little bit from this tolerance from 4.7 to 4.6, then we gain time to crossover. So we go down to 28 minutes. Of course, the gain that we get here is small, but this depends on the model instance. So this means that a readjustment of the convergence tolerance, it will need to find a nice trade-off between avoiding wasted iterations in barrier and also improving the starting point of the crossover algorithm. And the last point to speed up the crossover is to change the pricing algorithm of the Simplex algorithm that comes in the end by changing the options PPRint and DPRint. There are several pricing algorithms to be used. I'm not going now into the details for sake of time. But here, because we are using Primal, we are solving the Primal problem, maybe it's worthy to check different pricing algorithms for the Primal problem, for the crossover phase. And if we force here the steepest edge pricing with slack initial norms, this variant of the steepest edge pricing, if we force this, then the solution time is further reduced to 26 minutes because we have reduced the Simplex iterations after the crossover. This was a faster pricing algorithm for our model. And of course, the question is, do we keep now the crossover? We are at 26 minutes, or we disable the crossover and we drop to 18 minutes. And of course, we can see here that the change that we have in the objective function is very small. Of course, the solutions can be ugly. We cannot, if we solve mixed integer problems, if we do this approach, it's not good. And also it can be that the duals that we have without crossover can be a little bit different from the duals without the crossover. The duals without the crossover can be different from the duals with the crossover. And of course, without a basic solution, we cannot do a Simplex warm start. So this is my last point, the advanced basis to warm up the Simplex. So there is an option, advanced advint, that enables the Simplex, not the barrier. Now we are not doing anything now with the barrier. To use an advanced basis, which is a basic solution from a previous run that can be used for a warm startup. And here it's important to see if, when we change the model, if the solution that we have from a previous run is still feasible or not. And this depends what change we do in the model. And we can see here that depending on what we do in the model, if we add variables or rows, or we change coefficients in objective function or in the constraints, we retain some feasibility or we lost feasibility. So for example, if we add variables, we retain primal feasibility. In that case, using primal Simplex with an advanced basis will work. If we add rows, we retain dual feasibility. In that case, so if we add constraints, in that case, using dual Simplex with an advanced basis maybe works well, and so on. But there is also a case when we change the matrix coefficient of basic variables that the feasibility is lost and their advanced basis cannot be used. So this is quite important to know which feasibility is retained by when we do a change in the model if we want to use a warm startup for the Simplex algorithm, not the barrier. So this means that we change the LP method. We don't use the barrier anymore. So this is the end. So what we did, we start from a model we took 9 hours to solve, and we took 10 steps, which you can see here, to drop the solution time to 26 minutes. And if we disable the crossover, down to 18 minutes. So that's all from my side. And yes, I would like to thank Fred from GAMS and George from ETSAP for all the help that they provide to this presentation. So thank you very much.
Thank you, Vangelis. Thank you for your time putting this together.
And sorry for I'm always delaying my presentation.
No, but it's always interesting. So we have some hands raised. Paul, no, actually not hand. People are clapping. Okay, Tom, no comments, no questions.
Just one question.
Yeah.
Is it possible to have the video of webinar, because I'm late, please?
Yes, all our webinars are uploaded in our YouTube channel. So this will be uploaded in a couple of days as well, and the presentation as well. So you will be able to access the video and the presentation through our web page on YouTube.
Okay, thank you.
Okay. So questions, Tom.
Yeah, thanks, Vangelis. A very brief question. So the last thing what you described with the starting point, this is in GAMS, the save point option. And so where you save the last, the parameters of the last run, to use this as a starting point in the S point option, or what is this? Or is this now a separate, let's say, preference which you can tweak in CPLEX?
It is this is a solution point from the GAMS, which can also be enabled. I think also Times has some switches that can also produce that from the run file. So
yeah, exactly. Okay, good. Thanks.
X points, L point, or S points. I think we have it in the run file.
Yeah, exactly. That's what I meant. Yeah, thanks a lot. Okay, good.
Paul?
Vangelis, it was fascinating. I have a question. At one point you reduced the tolerance for barrier in order to reduce the number of iterations. Now, in quite a few runs I've had in the past, crossover takes a long time compared to barrier. And I've always wondered if it was worth trying to increase the tolerance of barrier to try and get closer to the solution.
Yes, thank you, Paul. In my presentation, we do both. First, we increase the tolerance to avoid wasted barrier iterations. This worsening a little bit the starting point of crossover. And then if we see that the crossover takes a lot of time, then we reduce the tolerance of the barrier in order to provide a better starting point to crossover. Of course, we have the danger if we reduce the tolerance too much, well below the default value, it can be that barrier reports our problem infeasible. But yes, of course, as you said, if a crossover takes a lot of time, it's usually because either the starting point is good, and this we can do it with the tolerance, we can reduce the tolerance. This, of course, could create some wasted iterations in barrier. So this is a trade-off all the time, or make the barrier to report the model infeasible. Or the second why crossover can take a lot of time is numerical difficulties. And for this, we need a separate webinar to go through that. It's a big topic.
There's a question in the chat, I guess. Maybe you can see that. Use of VEDA.
Where were you using VEDA or VEDA 2? No, I just produced the DD files, and then I was just running directly with GAMS. I was not always going through the solve from Veda. Not speed differences. No, in terms of GAMS, not. I haven't noticed, but I have to say, I don't know if we should expect this. I'm not so sure. I guess that speed differences mean in the solution time, not in creating the DD files, because creating the DD files Veda 2 it's much faster.
Good. So I don't see any other hands raised or any other questions. So for those of you that were brave enough to stay until the end of the webinar, do you think that it would be interesting to have a second webinar on numerical difficulties, as Vangelis mentioned? So if you just put your thumbs up, I think that would be a good indication. Okay. Yeah, we do have some positive reactions on that. So, okay. So we'll coordinate with Vangelis to organize another webinar looking into the numerical difficulties then at a certain point. So we'll give you some time to rest after this, and then we can organize another webinar. So thank you all for participating. Thank you, Vangelis, for this very interesting analysis.
Thank you, George, for the opportunity. And closing this, I would just like to note that, of course, this parametrization that I showed is quite, let's say, extreme. Okay, we don't need to touch all these options to make our models. Of course, it depends also on the model instance. So in my chart that I presented in the end, which we can see it in the video and in the presentation, you can see that some steps perform better in terms of performance reduction, solution time reduction than others. But this depends on the model instance. That's only, and I'm happy also if you have questions, please feel free to drop an email. And yeah, thanks a lot for attending.
Great, thank you, Vangelis.
Thank you.
So we will put this on the website, as I said, and both the presentation and the video with a link on YouTube, so you can revisit if you want to see the details. Thank you all.
Okay, thank you.
Bye-bye.
Bye.